I was trying to say that we were here also in 2016 for the 9th edition of the ESMolNa. Here you have Mariluz, Celia, and Paco taking care of everything at the beginning of the school. Mariluz with the students. You're the main actors of the school. Then put questions, please. And here you have the whole group with, there you have Mariluz and Eugenio with the whole group. And the next picture is a picture that Mariluz likes very much. We were having a beer at the Plaza Mayor and with the physics team, speaking about spin ups and spin down. Also, Eugenio was there. And that was at the end of the school also with the physics team. And I would like also to mention the nice evening we had at having a wine tasting at Los Toreros. And here I would like to dedicate a memory to two nice and very close people, José Antonio de Saja and Catalina Ruiz. Here you have with Eugenio. We enjoyed them in the ESMolNa, but they passed away a few years ago. Okay. It was not planned that I gave a lecture here. Maybe that was the reason for the problems with the computers, but finally Eugenio decided that I should come. And he told me that I have to speak about optical properties. The last time I was here, I was speaking about the supramolecular organization of molecular materials. Then I decided to recover this, this field we have been working for years in the this kind of materials, ionic transition metal complex as electroluminescent materials. I will give an idea about electroluminescence, the main concept. I will compare these two kinds of devices, LEDs versus OLEDs. And I will speak about the stability and efficiency of these devices and also how to tune the emission color. If we are not very tired, at the very end, I will show an example of high performance complexes in this kind of device. Then the concept of luminescence is the emission of light by a material that has been previously excited by an energy source. And chemists, we know very well the process of photoluminescence. Here you have a rhodamine or a fluorescein solutions. Then here you have an ultraviolet lamp. They are absorbing the photon from the ultraviolet lamps. I mean that the excitation source is the light, the photons, and they are emitting light in the yellow or in the green. The molecules are in the ground electronic state. They are excited to the singlet or triplet excited state, and then you obtain fluorescence from the singlet excited state or fluorescence from the triplet excited state. In electroluminescence, the excitation source is an electric field, and this is the simplest device, the LED lamps. We are transforming electric energy into light energy. And in 1990, for the first time proposed an organic LED. In organic LED, what you have is a transparent support like glass. The anode is indium tin oxide, and over the anode you have the luminescent material. In this case, is a conjugated polymer, a conducting polymer, PPD. Over the luminescent material, you have the cathode, for instance, barrier. And when you apply the voltage, you are oxidizing the material here, you are introducing the holes, and reducing the material here, you are introducing the electrons. The holes and the electrons combine, and then you obtain the light, in this case, green, yellow. And the emissive excited state is the same as in fluorescence or phosphorescence. And OLEDs have the advantages of being luminescent surfaces, and they can be also flexible. You have OLEDs now in almost every device with a display. But they are quite costly to prepare, because they are multi-layer devices. You have to deposit by vacuum different layers, and you have that the cathode is not stable to the air. Then you need rigorous encapsulations. There is an alternative for OLEDs that are these devices, light-emitting electrochemical cells, the LEDs. The structure is similar, but you have two main differences. The first main difference is that here, as luminescent material, now you have an ionic material. For instance, this ionic transition metal complex, ruthenium 3-bipyridine. And now, as a cathode, you have a noble metal, like gold, silver, or aluminum. Okay. This is more or less the mechanism, simplified, of a LED device. At the beginning, you have that you cannot inject the electron from the noble metal to the LUMO because it's too high in energy. But the difference is now when you apply the voltage, because you have an ionic material, the ions can move to the electrodes. And then you reduce the barrier and you can inject easily the charges. Then you do the oxidation at the anode, you inject the holes, the reduction at the cathode, you inject the electrons, they move along the material and they recombine forming excitons, molecules in excited states. And finally, you have the emission of light, in this case by electrophosphorescence, because are the triplets of the complex who are emitting the light. And very important is that this material, the ionic transition metal complex, is doing all the processes in the sense that it's taking care of the charge injection, of the charge transport, and also of the light emission. Then, when you combine two electrons in two levels, you have these four possibilities. I mean, only one singlet or three triplets. I mean, statistically, you have 20%, 25% of singlets and 75% of triplets. In OLEDs with organic molecules by fluorescence, you can only provide of the 25% of the singlets. But in LEDs, due to the efficient intersystem closing, you are working with transition metals, you can populate the triplets and you can provide 100% of the excitons. And you are working with electrophosphorescence emitting from the triplets. Okay, then you have these two kind of devices, the OLEDs and the LEDs. The advantages of LEDs, they are monolayer. Here you have a multi-layer. Air-stable electrodes, here air-sensitive electrodes, easy to prepare because you prepare from a solution. But you have also a limitation. The limitation is mainly the slow turn on of the device, easy to the range of colors. Blue is quite difficult to prepare, the short lifetimes, the stability of the device, and also the low efficiencies. Here you have, for instance, the performing of this simple LED device with ruthenium trees by pyrite. Here in orange, you have the current density, and in blue, you have the light emitted by the device, the luminescence, against the time. And as you can see, the first problem is the turn on time. You need 40 minutes to reach the maximum emission. Second problem is the stability, the lifetime. In only 12 hours, you have only half of the light emitted. Other problem is the efficiency. The external quantum efficiency is lower than 1%. That means that you put inside 100 electrons and you obtain less than a photon. And finally, is the color. Blue is quite difficult to obtain. Okay. We are going to speak about the stability efficiency very quickly and also about the emission color. We are a theoretical group, and then our main goal is to characterize the states, the lower energy electronically excited states that are playing a role in the device. That means to state the nature and also the relative energy of the different states. This is ruthenium trees by pyridine. It has an octahedral structure, geometry. And the first thing we do is to look at the molecular orbitals. Here is very simple. The HOMO -1 and HOMO -2 correspond to the 2Tg d orbitals of ruthenium. And the LUMO correspond to the pi orbitals of the BP ligands. And over these orbitals, you have the antibonding, they have been already mentioned, the antibonding AG orbitals of ruthenium, 2.2 electron volts above. Now, those are molecular orbitals, but we are interested in electronic states. Then we calculate the triplets at the geometry of the ground state of the complex. And we have many, many excited states. Then the first 9 states corresponds to transition from the HOMO -1, HOMO -2 to these 3 LUMOs. That means that you are really transferring an electron from the metal to the ligands, and you have a metal to ligand charge transfer triplet state. Above those states, you have the transition from these T2G orbitals to the EG orbitals. I mean, there is a transition mainly localized on the metal, a metal-centered triplet, a DD star transition. But one important thing is, when you speak about orbitals, the difference here is 2.2 electron volts. When you speak about electronic states, the difference is only of 0.7 electron volts. We can optimize also the geometry of the excited, the first triplet excited state. And what you find is that that state corresponds to an electron promotion from the HOMO to the LUMO. Clearly, you are transferring an electron from the metal to the ligands. You have a metal to ligand charge transfer state. And here you can see the spin density, 1 ampere electron is over the metal, and the other electron is localized over the ligands. Okay, we can play also with those orbitals that Eliseo mentioned, I mean, to transfer one electron from the HOMO to those EG unoccupied orbitals of the metals. And here, look that you have antibond interaction between the metal and also those nitrogen atoms or those nitrogen atoms there. Then, when you promote the electron, due to those bonding and those antibond interaction, this bond lengthens these bonds in axial positions. And when you promote the electron to that orbital, then the bonds in the equatorial plane, they lengthen. You are increasing the size of the complexes. You are actually opening the complex. Then the population of those DD star metal-centered triplets implies that you are really opening the structure of the complex because those bonds now are longer than in the ground state. And from the energetic point of view, the situation is the following. At the ground state geometry, really the metal-centered state is higher in energy, 0.7. But when you relax the geometry of that state, it goes down below the triplet metal ligand charge transfer, and then this state is 0.5 electron volts below that one. That means that that state can be populated by internal conversion. And finally, this state is close to the ground state, and it really acts as a quencher of the emission, a non-decay transfer to the ground state. Then, the existence of these DD star metal-centered triplets has an influence in the performance of the device. First, because it quenches the phosphorescent emission from the metal to ligand charge transfer state. And that is the reason for the low external quantum efficiency. And the second reason is because you are opening really the structure, and then small molecules like water can enter into the structure and move this ligand, and these species have been shown that they are formed and they quench also the emission. Okay, then we have a problem with this complex. How to solve that problem? The solution is to move up these metal-centered states and to move up and then avoid this internal conversion. The way to do it is to change from the second to the third row of the transition metals. I mean, to use, for instance, iridium-3 complexes. And these are actually the complexes that have been more used in this kind of devices. These are heteroleptic iridium-3 complexes. You have one neutral ligand by pyridine, BP, and two negative charge ligands, phenylpyridine, PP. And then in this complex, there is a very important difference against the ruthenium complexes, is that the HOMO is localized now on the metal, but also on the phenyl rings. And the LUMO is fully localized on the BP ligand. And the first triplet state also corresponds to a HOMO-LUMO transition that now involves a transition from the metal to that ligand and also from these ligands to the other ligands. We have a charge transfer, metal to ligand, and also ligand to ligand state. Then the emission will take place from this metal to ligand charge transfer state and takes in the orange. You can see here the theoretical prediction, and you can see here the photoluminescent spectra. It's in very good agreement, it's emitting in the orange. And a very important thing also, when you have emission from this kind of charge transfer states, you always have a very broad band, non-structured band. This is very typical. Okay, now we're playing with these heteroleptic iridium-3 complexes. They have also DD states. And when you populate these DD states, you open the structure of the complex. We are in the same problem. No, because now those states are higher in energy. I mean, we have moved the states to higher energies over the meeting state. Those states will not be populated. And in the device, you feel the difference because now, before we have only 12 hours, the lifetime, now the lifetime is 600 hours. But there is always a but. Now the turn on time is 50 hours. You need 50 hours to reach the maximum of the emission. Then to solve that, you have to add ionic lipids to increase the concentration of ions in the device. In that way, The ions move quickly, and the turn-on time reduces. But again, you reduce the turn-on time, but also the lifetime. Okay, I will not enter in all the steps in that to solve that problem. Finally, using more bulky groups in the molecule, but mainly changing the driving mode of the device. I mean, the driving mode, this block wave pulse current driving is you put the intensity, the current, but you stop the current doing duty cycles. And then you stop really the growing of the doped zone. In that way, you really make you have devices with an instant high luminescence of less than 1 second. The light emitting is quite high, almost 700 candelas per square meter. And the most important, look at the light emitted. The luminescence is stable along the time. You have thousands of hours the device is emitting the light. Okay, we have solved more or less the stability, the efficiency of the device. Now we change how to change the color of the device. And here really to work with iridium complexes is very nice, because I tell you already, the HOMO is localized in this part of the molecule and the LUMO is localized in the other part of the molecule. Then for the chemist, it's very easy to change the energy of the LUMO, the HOMO and the LUMO only by putting here substituents or here, or changing the structure, the chemical structure of the ligands. In that way, we change the energy of the HOMO and the LUMO, and we change the emission color. It's very important to have emission in all, at least blue, red, and green, to have the white. Okay. The most difficult troop time is the blue emission. And the strategy to do that, usually you have to increase the HOMO-LUMO gap. And usually the people have done is to modify the structure of the main ligands, the CN ligands, by introducing electron withdrawing groups like fluorine here, or by reducing the size of this pyridine ring, the nitrogen containing ring. And I will show you an example of doing that, making also theoretical calculations and comparison with the experiment. Look, in this video you have, this is the archetype complex we are using as a reference, and we are changing the pyridine ring by an azole ring with an increasing number of nitrogen atoms. Okay, here you have the HOMO and the LUMO of the system, and when you start to, you put the azole and you start to increase the number of nitrogen atoms, you do that. You are stabilizing the HOMO very nicely. What you will expect for the LUMO is localized on that ligand. You have changed nothing in that ligand. Then the LUMO remains the energy almost constant. Then you are increasing really the HOMO-LUMO gap, and you can expect a blue shift of the emission along this series. You can calculate as before the lowest triplet excited state, I mean the emitting triplet state, and you can see that the topology of that state is the same. I mean, you have a metal to ligand, ligand to ligand charge transfer. And when you calculate the emission energy, you can see that really you are shifting the emission to the blue. This is the theoretical value, this is experimental value, they are in quite good agreement. Okay, and now we go to the experiment, the data we have in the literature. This is our archetype, our reference compound. You go to here, and the emission is shifted to the blue. You go to this tetrazole, and the emission is shifted to the blue, not very much. And you go to this with a triazole, and the emission is not shifted to the blue with respect to this one. Then experimental data is suggesting that a higher number of nitrogen atoms in the azole ring does not ensure an increase of the emission energy, the blue shift. But look, here you are comparing things that are not really the same situation, because now here the azole ring is linked by the nitrogen, but here and here they are linked by the carbon. Then we propose to study this series, that the difference with that before we studied is that here we have a carbon, not a nitrogen. And here, when you start to increase the numbers, first you increase the energy of the HOMO, and after that you decrease when you increasing the number of nitrogen atoms. Then the situation is that the LUMO remains constant as before, and the situation that first you shift to the red and after that to the blue. The conclusion is you have the blue shift, yes, but now the HOMO-LUMO gap are 0.3 EVs smaller than before. Here you can see, this is the series with the nitrogen linked, and this is the series with the carbon. I mean, you have always the shift to the blue, to the lower wavelengths, but here a redshift with respect to the other series. I mean, that the conclusion we infer from the experimental data was wrong in the sense that we were not comparing the same situation. If we compare this with this, I mean, triazole with tetrazole, the shift to the blue is occurring. Okay, what will happen if we introduce the acyl rings in the N ligand, in the bipyridine ligand? I mean, substitute one of these pyrene rings by an acyl ring. We should expect also a blue shift. Look, that was what will be the situation. This is our reference compound, and then now the HOMO doesn't change in energy because we are not changing the chemical structure of those ligands. We are changing the chemical structure of this ligand. And here what happens is that the first, it goes up, and after that, always increasing the number of nitrogen atoms, you stabilize. Then you have this blue shift, but you, along the series, you obtain a red shift. That means by doing very simple chemical changes, you can modulate the light emitted to the blue, introducing the acyl ring in the main ligands, or to the red, introducing in the bipyridine ligand. Okay, that was an strategy. And this was another possibility. This possibility is to change one of those pyrene rings by a carbene unit, like here. And you can also put here the fluorine atoms to shift to the blue. And here you have the experimental result. Those complexes were synthesized, and you can see here, this is the photoluminescent spectra with the substituents being hydrogens or being fluorine atoms. And the first thing is that you have an structure emission band. Okay? And the second thing, you are in the blue, you are around 450 nanometers. They are emitting in the blue, but the light emitting is very, very, very low, around quantum yield of 1%. And actually, when you put those complexes in legs, you have no light. I mean, in the device, you obtain no light at the end. What's the reason for that? Then, the question is that here, everything has changed, because now both the HOMO and also the LUMOS are localized mainly on the main ligands. That means that now the emitting state, the lowest energy triplet state, is a ligand-centered state. And then there is the reason because you obtain that structure band, emission band. For transition, for charge transfer state, you have a broad band, and for ligand-centered stage, you have this structural band. And if you optimize that state, the lowest state, you can see here that the ampere electrons are mainly localized on one of the main ligands. But even more important, you have also a metal-centered state, because in those molecules, the difference in the coordination of the carbene unit and the pyrene units here leads to that in the excited state, the pyridine rings prefer to turn, and you have finally the metal that is pentacoordinated. And this metal-centered state is very close to the ground state, and then it quenches the emission. That is the reason because these molecules, these complexes, emit almost no light. I mean, there are different strategies to change, to modulate the color, but the nature of the state, being ligand-centered, metal-to-ligand charge transfer, or metal-centered, plays a very important role in the emission you have. And finally, and very quickly, I will show you an example of complexes that really work very nicely. This series of complexes were synthesized by a group in the University of Burgos, and the strategy was to substitute one of the pyridine rings by an imidazole ring or a benzimidazole ring. In those complexes, you have also a thiazole ring, from 1 to 5. They are incorporated in leg devices, and the behavior is completely different, the results you obtain in the device. Because for one, the luminescence is very low, and the lifetime only 2 hours. For complex 5, the luminescence is also low, the lifetime is larger. And when you go to the complexes with the benzimidazole unit, but not the thiazole, you have the luminescence has increased 1 order of magnitude, you have high luminescence. And the most important is that in this complex, complex 3, the luminescence is very stable. You have the lifetime is 1,000 of hours. They have arrived until 10,000 hours. Why that big difference between the complexes? Again, the difference is due to the nature of the triplet excited state, the state from which you have the emission. You can see here the orbitals. The HOMO along the series is almost constant in energy. Why? Because you are changing that ligand, not this ligand where the HOMO is localized. Those orbitals, LUMO plus 1 and LUMO plus 2, they also the same because they are localized on those ligands. And the LUMO, which is localized in the ligand where you are doing the changes, is stabilized when you put the imidazole rings, the benzimidazole rings, and it is destabilized when you add the thiazole ring. Those changes are very important in fitting the nature of the excited state, the emitting excited state. Those are the triplet states. And the situation is very difficult because very different because you have for 2 and 3, the lowest triplet state is a metal to ligand, ligand to ligand charge transfer state. When you go to 4 and 5 with the thiazole rings, those states are pushed up in energy due to the changes in the LUMO, and now the emitting state is a ligand-centered state, localized on one of the main ligands. And for 1, you have a mixture of both because are almost degenerate. And that changes completely the emission properties, because in that case, for 2 and 3, no thiazole, then you have a metal to ligand, ligand to ligand charge transfer state, and you have this broad band with almost no structure, and it has a large rigidochromic effect. That means that when you decrease the temperature, then it shifts to the blue. By contrast, for 4 and 5 with the thiazole, you have a ligand-centered emitting state. You have this structure band with no rigidochromic shift, and then this is a ligand-centered emitting state. High luminescence, low luminescence. And if you look to the redox properties, 1, 2, and 4, you have that the reduction of those complexes, 1, 2, and 4, is irreversible. And that means that they will be not very stable in the device when you inject the electrons. By contrast, 3, you have a fully reversible reduction, and it will be more stable. 5 is a special case. This reversibility gives good stability to this complex when you are in the leg, operating the leg. And that is the reason for the high stability. Okay, this is the last conclusion. This complex exhibits, is not the best one, but exhibits record performance in the sense that it presents simultaneously high luminescence and efficiency, short turn-on time immediately, and high stability, almost 3,000 hours. And I would like to remark that here, theoretical calculations are very useful because they can determine the nature and also the relative energy position of the states that are playing a role in the emission in the device. Okay, I would like to thank the collaboration, especially with Henk Bolling. Henk is also from the ICMol. He's working there. And we have been working in very close contact almost for 20 years. And also to the other collaborators in my group. And before finishing, I would like, this morning we were with Herre in the way to here. He was quite interested in the visit we did, the tourist visit. I would suggest that at the end of this school, take your time also to visit some places near here, because you are really in a very, very nice place. Near here, that means Valladolid, Valencia, and things like that. We did it in 2016, and we enjoyed very, very, very much a very nice excursion. The first place we visited, that was not the first, but this is a very nice Romanic church, San Martin de Tours at Fromista, from the 11th century. Very nice. Also taste the wine and the cheese, please. This place is in the St. James Way, And this is a Templar church. It's Santa Maria la Blanca in Villalcázar de Sirga from the 12th century. Of course, if you are with Eugenia, you have to stop to taste some lamb. That's very important. And that is a very, very unique, not nice, unique place, because this is a Visigothic church from the 7th century. Very nice place, and thanks for your attention.
I'm sorry for the time.
Thank you. It's really impressive how you are able to fine-tune the electronics. I was wondering about the stability, because you mentioned at the beginning with the ruthenium complex the problem of water, right?
Yeah.
But not at the end with iridium. So there's no problem, or you can just solve very easily just with steric hindrance in the ligands? Or?
No, the question there was to push up the metal-centered states. Because if they are up, then you don't populate those states. That means that you not open the structure of the complex, and it is more difficult that small molecules enter into the structure of the complex. Even that would be the case if you protect the complex with bulky groups, but that is not only for stability, because if the complexes are very near one from the other, then due to the interaction between the complexes, then you quench also the emission. Then you obtain more efficient complexes if they are with bulky groups that put apart a little bit. I mean that the bulky groups was not really the reason for the stability, it was also for the efficiency of the device.
But it was only in the ruthenium, not in the iridium.
No, that was with iridium.
Oh, okay.
And with iridium, the problem is not so high because now the metal center state are up in energy. In ruthenium, you have the metal central complex that are lower in energy than the emission, that the emitting state. Then you populate them. In the iridium complexes, they are up in energy, higher in energy, and then it is more difficult to populate those states.
Okay, thank you.
And another question. You have more questions for Enrique? Yeah, Roberta. Vamos a ver, pero ¿cómo me pasa siempre por ahí por medio que es imposible?
Es que está Eliseo también preguntando.
Just a second.
Es imposible pasar de una parte a otra.
Thank you, Enrique, for the nice presentation. I have a question. In your presentation, you focus mainly on energies, calculation of the energies. My question is about other experimental parameters like lifetimes or quantum yields. Which is the state of theoretical methods, DFT or post-Hartree-Fock, to determine such experimental data?
Okay, we are now we are re-studying some of the complexes, because at that time we were strongly collaborating in a European project with experimental groups, and they were not so lucky if we started to do more accurate calculations. Then we did only DFT calculation. And at this moment, we are also calculating the connection between the different kinds of states and also the barriers. And then we are obtaining data to obtain the lifetime in the different states, but not the quantum yield for the moment. It is possible to have an idea about the quantum yield, but we have not yet estimated. We have estimated the lifetime in the different states. But to do that, we have also to calculate the barriers between the states and the conical intersections.
Roberta.
It's very, very, very nice talk. I'm wondering, all your devices have are liquid. They contains the active part is a fluid solution.
No,
completely. No.
They deposit from solution, but after that they do annihilation and the solvent is eliminated.
Completely. Okay.
I mean, you have a solid state lighting device.
Completely. Okay. Thank you.